So far we have considered 4 different Fourier representation. We started with a continuous time Fourier. We started with continuous time Fourier series xt Fourier series with some period t naught ak. That is for the variable here in the time domain is continuous, and it is a periodic function. Xt is it is a function of a continuous variable t, and then it is a periodic function, isn't it? And Fourier series coefficients are, this is discrete because it is a sequence function of k, and then is it periodic or aperiodic for a continuous time signal?
Aperiodic.
It is aperiodic. Okay. Then we discussed discrete time Fourier series. In discrete time Fourier series, actually, it is if we have a signal, periodic signal xn, and we denote by ak, it's Fourier series, and xn is it is a function of a discrete variable, so we can write discrete, and it is periodic. And what about the Fourier series coefficients? Fourier series coefficients also, this is also a sequence, so it is discrete and periodic, isn't it?
Yes, sir.
It's periodic. Okay. Then we discussed about continuous time Fourier transform, that is xt Fourier transform, it is denoted by x of j omega. Here it is a function of a continuous variable t, so it is continuous. And is it periodic, or generally it is aperiodic? And in some generalized sense, we can find the Fourier transform for periodic signals, but it is an aperiodic signal. What about this x of j omega? It is function of a, what is the nature of this variable omega?
Continuous.
Continuous. And is it periodic or aperiodic? It is aperiodic, isn't it? And finally, we discussed discrete time Fourier transform, where xn, here it is discrete, aperiodic. And what about this? What is the nature of this x e to the power j omega? It is function of a continuous variable. And is it periodic? Is there any periodicity in the Fourier transform of a discrete time signal?
Yes, sir.
It is periodic, isn't it? Because it is 2 pi periodic. Now we already discussed the duality. Which duality we have discussed? We discussed this duality. There is a duality here: continuous aperiodic, continuous aperiodic. So we have already discussed that duality. So is there any other? Can you identify any other duality here?
DTFS.
DTFS. There is a duality here. Okay. So I'm just stating that duality. It is straightforward. It is straightforward to derive that duality, and I think that proof is given in the textbook also, not in Oppenheim. I think in Simon Haken, all these dualities are mentioned. So if you want to read more about the duality properties, please refer to Simon Haken. It is given in detail. Okay. So I'm just stating that if xn, and those who are following Simon Haken, you know that there is a different Simon Haken uses a different notation for ak. It uses, anyway, it is a sequence. This is the notation. Okay. So for describing the duality property, it is convenient to use this notation where xk, let us denote it as xk, capital Xk. Okay. So the duality property, this is a discrete, remember this is one discrete sequence and this is another discrete sequence. Okay. Now, if we have a signal in the time domain having this shape, that is capital X n. Okay. If we have a signal in the time domain having this shape, then its Fourier series, it is discrete time Fourier series, and this is with respect to some period n. This will also be periodic with same period n, and its Fourier series coefficients are given by 1 by n x of minus k. Okay, there is a flipping scaling factor 1 by n. Now, can you identify any other duality here?
So CTFS to DTFT.
Sorry, is there any duality here? What is this? If we have a periodic signal xt, its Fourier series coefficients are discrete anyway. It is for Fourier series coefficients. It is a series, so discrete and aperiodic. So here, if you consider a discrete sequence, discrete time signal, its Fourier transform is function of a continuous variable and periodic. So there is a duality. So let me explain that duality. You consider some sequence, okay, some aperiodic signal, aperiodic sequence, and if you take the discrete time Fourier transform of that signal, and you get some periodic, there is 2 pi periodicity, isn't it? I am just drawing something like this. Let's say this is a 2 pi periodic function. This is 0, 2 pi. Okay. This is a Fourier transform spectrum of that signal. Now, if we consider a signal having this shape in the time domain, we can always have a signal with this shape in the time domain, isn't it? Is it? If we consider a signal having this shape in the time domain, which Fourier representation we can have for that signal? If it is a periodic signal, continuous time periodic signal, isn't it? If we consider this shape in the time domain, means it is function of a continuous variable. So if we consider that shape, a signal having this shape, a periodic signal having this shape in the time domain, what is the Fourier representation? For continuous time
Fourier series.
periodic signal, it is continuous time Fourier series, is it? So
Yes,
we will
sir.
get, if we take the Fourier series of this, we get a sequence AK. Now the question is this AK related to this? This is also a sequence. Okay, that is the duality. There is a duality. So I'm going to prove that. Consider a discrete time signal xn, and let's say its Fourier transform is x e to the power j omega. Okay, and this is summation over n. Is it? Now, if we consider a signal having this shape in the time domain, that means I am replacing this omega with t. We get a signal e to the power jt. Okay, signal having this shape in the time domain. Is it a periodic signal?
Yes, sir.
We can find a Fourier series with respect to what is the period.
2 pi.
Period is 2 pi. Its fundamental period is 2 pi. Let's say AK are the Fourier series coefficients. Okay, we consider a signal having this shape in the time domain. We can find a Fourier series representation. What does this mean? we can write x e to the power jt as what? What is the Fourier series summation? Ak into e to the power j 2 pi by what? 2 pi by? What is the funda? 2 pi by t naught, isn't it? What is t naught here? Is it this Fourier series summation?
Yes, sir.
This is the Fourier series summation, right? So we can write this as, I am writing this here, x e to the power jt is equal to summation over k ak e to the power jkt. Is it? That is the Fourier series summation. If ak are the Fourier series coefficients of this signal, this is how we express that signal x e to the power jt as a linear combination of complex exponentials. That is Fourier series summation. Now this is x e to the power j omega, isn't it? What is x e to the power jt? If you put t equals to omega here, omega is equal to t here. I'm putting omega equals to t here. Is it?
Yes.
Yes, sir.
So if you look at these two equations, left hand side is the same, isn't it? So this must be equal. Now tell me what is AK?
X of
Xn.
Is it xn or you
X
take
of minus n.
it is, can we
X of
write it
minus
is
n.
x of minus k?
Yes, sir.
AK is x of minus k, isn't it? That is the duality property. So let me write the duality property here. If we consider a sequence xn, discrete time signal xn, and let's say x e to the power j omega is its Fourier transform. So this is again like when I explained the duality property of continuous time systems, I have told you that don't think that this capital X is something associated with the Fourier domain. Okay, it is mapping from one function to another function. So think it as two functions. So now if we have this function in the time domain, that means a signal having this shape in the time domain, x e to the power jt, then what is its Fourier series coefficients? We can find the Fourier series with respect to period 2 pi. What are its Fourier series coefficients? Is it that? That is the duality we have proved. So consider a signal having the same shape in the time domain. Its Fourier series coefficients are flipped version of this xn. Is it? And in some textbooks, this duality property is given as x e to the power minus jt ak is equal to xk. Both are same, isn't it? Are they same? They're same because if you replace with t with minus t, we know the property of Fourier series k will be replaced with minus k. Okay, if we flip the signal in the time domain, there is a flipping in the frequency Fourier domain also. Okay, so this is the duality property.